We begin our last unit of the class, last two class periods. You are almost there. So we're going to get there. Okay. Today we are talking about transition metal chemistry and new carbon-carbon bond forming reactions. This is going to involve some stuff you probably never thought about before, but with just a little bit of background you can understand it, and these are really, really useful reactions. Of everything we've discussed this semester, a reaction I will tell you about today is by far the most used in the pharmaceutical industry because it just works that well. I want to introduce transition metal chemistry with a cute little reaction called cuprate coupling. And it involves a reagent that you've seen before. You saw cuprates in chapter 13 of this class, where you learned that cuprates will add to acid chlorides to give ketones without going on to the alcohol. And you learned that cuprates will also add to the beta carbon of an alpha-beta unsaturated carbonyl compound. And I'm drawing this complex with a little bracket with a negative charge to indicate the overall charge is negative. Normally we drew that negative charge pretty close to the copper. And I told you in chapter 13 that you can think about this reagent as though it were just a carrier of an anion. And you're going to see today that that was true from a certain point of view, to use OB1's cop-out excuse, but it doesn't actually capture all of the features of what's going on with cuprates. So in the cuprate coupling reaction, you can take an alkyl halide and you can make a new bond between one of the benzene rings on the cuprate and then the carbon that bears the halide. So here's the carbon with the halide. This is the carbon that used to be attached to copper. Here is the new bond we made. And we call that a coupling reaction because two carbons that didn't used to be bonded to each other are now bonded to each other. Now, at first glance, that looks like you could propose an SN2-like mechanism. Perhaps you could have the negatively charged carbon on that benzene ring do an SN2 reaction like that. That seems to be a reasonable mechanism. If you think about the cuprate as a carrier of anions, you could imagine doing here what we used to do for Grignard additions to carbonyls. That is, the carbon leaves the metal and then attacks the antibonding orbital and breaks the carbon halide bond. That's simple, it's easy, it makes sense, and it is wrong, unfortunately. So how do we know it's wrong? And the reason we know that it's not SN2 is because you can swap which group is on which side of this reaction. You can put the alkyl groups on the copper. You can put the halide on the benzene ring, and it still works. You can still couple the blue carbon on the benzene ring. Oh, I guess I don't need to draw it again. I just need to draw my arrow longer. Now, why does this example below rule out SN2? Go ahead.
Because we can't do backside attack on that BR group.
Right, so an sp2 hybridized carbon bonded to a halide, especially with the benzene ring, backside attack in an SN2 reaction would require you to actually get into the middle of the benzene ring. You simply can't. And we've said before in 351 that you don't do SN2 or even SN1 at vinyl or aryl halides. And that's because the corresponding carbocations are too unstable and because the antibonding orbitals are inaccessible. So it can't be SN2. It has to be something else. And before we tell you what that something else is, we need to do a little bit of background on transition metals so you can understand what the possibilities are. Transition metals are complicated, not only because they've got more electrons available, and we haven't done anything with them so far this semester, but also because the ways of drawing transition metal complexes differ in subtle but important ways from how you've typically drawn carbons. For example, or organic molecules. In every organic molecule structure you've drawn before, you've had to put formal charge on atoms, right? That's been an absolute requirement. Not such a requirement for transition metal complexes. So let me take you through some basic background on transition metals so we can have it, so we have the background to understand what the mechanism is for this cuprate coupling reaction. So we're going to start with scandium, which has 3 valence electrons. Then you've got titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, and zinc. And that goes from 3, 4, 5, 6, 7, 8, 9, 10, 11 to 12 valence electrons. Salud. All right. Other metals that typically show up, we're not going to be dealing with all of these, but another that show up in organometallic chemistry include molybdenum, ruthenium, which is 1 row down from iron, osmium, which is 1 row down from ruthenium. You've actually seen osmium tetroxide do some chemistry in 351, though you didn't worry about the metal at all. Below cobalt is rhodium, and below rhodium is iridium. We won't do a lot with rhodium or iridium, but there are a lot of people that do. Much more common is palladium, and then same column, more expensive than palladium, is platinum. There are a lot of people working in this space, but for us, and you're always going to have access to a periodic table, we're going to just want to know how many valence electrons does a metal come with when it's neutral, because we're going to use that to make some decisions about what the oxidation state of the metal is and how many electrons the metal can have. All right, let's look at some organometallic complexes, and we're going to introduce the concept of metals versus ligands. An organometallic complex is a complex that has a metal and carbons or other things. So here is a complex between palladium and 4 triphenylphosphine groups. What is triphenylphosphine? The pH means a phenyl group. The P is phosphorus. Triphenylphosphine is 3 benzene rings attached to phosphorus with the lone pair on the phosphorus. Now, if you look at that, if you look at the way I've drawn this, something should make you immediately uncomfortable, and that is phosphorus is bonded to 4 things. Now, normally when phosphorus or nitrogen are bonded to 4 things, it should have a positive formal charge, right? Nobody cares in organometallic chemistry. And the reason is that if you put positive formal charges on all of those phosphoruses, it would mislead you about what the chemistry actually is. And so we have a different, more intuitive way of thinking about electrons with organometallic complexes. We're still going to keep track of all of them, but we're going to lose formal charge on individual atoms because that doesn't end up being predictive of where the electron poor versus electron rich parts of a molecule are for organometallic complexes. So the first thing you need to know is the most obvious thing, and that is that the palladium is the metal and that the triphenylphosphine is what we're going to call a ligand, or something that is bound to the metal. And we're going to say that the ligand owns the electrons in the metal ligand bond. And we're going to see that there are 2 types of ligands. There are L-type ligands, and then there are X-type ligands. L-type ligands are, and the way to determine whether a ligand is L-type or X-type is simply to take the ligand and have it leave the complex with its electrons from the metal-ligand bond, and then determine whether that ligand is negatively charged or neutral after it has left. In this case, when triphenylphosphine takes the electrons from the metal-ligand bond and leaves, it leaves as a neutral molecule, and therefore it is an L-type ligand. Okay? So we would call triphenylphosphine an L-type ligand. The complex, which was neutral to begin with, you can tell it's neutral because I didn't draw an overall charge on the complex, is still neutral after the triphenylphosphine leaves. Okay? Neutral ligands typically include things that have lone pairs. Some examples of neutral L-type ligands would include things like phosphines, also amines based on nitrogen. Water can be a neutral ligand. Carbonyl lone pairs can be a neutral type of ligand. Also, pi bonds can be a neutral ligand, though how you draw the metal-ligand bond when it's the pi electrons that are interacting with the metal is a little bit challenging. But anything that can leave as a neutral group from the metal is an L-type ligand. X-type ligands, in contrast, leave as anions. So an X-type ligand leaves negatively charged. For example, we'll just modify one thing about this palladium complex. We'll use a Br on it. Actually, sorry, I want to do two things on this palladium complex. We'll put an alkyl group and a bromide. And to determine whether something's an X-type ligand or not, you think about what it would be like if it left. The complex is neutral to begin with. If the bromo ligand left, it would be negatively charged and the overall complex would be positively charged. So examples of L-type or X-type ligands include halides. Hydroxide can be an X-type ligand. How about this alkyl group? What kind of ligand is that? If it were to take these electrons and leave, what would it be? It'd be anion. It would be negatively charged. So that's how you can tell it's an X-type ligand. Okay, so alkyl groups are X-type ligands. Anything that when it leaves would be negatively charged is an X-type ligand. Now, why are we talking about that? Well, we're going to use the overall charge on a complex and the identity of the ligands to determine what the charge is on the metal and therefore what its oxidation state is. That's going to be important in following along what happens in some of these reactions. So let me give you a complex. This is different from the palladium complexes that we've talked about, but let's just do this briefly. This is cobalt bonded to 6 molecules of NH3 or ammonia. The geometry of this cobalt complex is more complicated than any geometry you've seen in this class so far. That's actually called octahedral. surrounded by 6 things. You've got axial ligands and equatorial ligands. The overall charge on this complex is 3+. Now, what kind of ligand is NH3? Right, because if it left, it would leave as neutral ammonia, which is an L-type ligand. So I have 6 L ligands. The overall charge on each of those ligands is 0. The overall charge on the complex is +3. Therefore, what is the charge on the cobalt? What does it have to be? Has to be +3. You know that because all the ligands are neutral. So the oxidation state of cobalt is +3. Now we can determine how many electrons cobalt has, knowing that all of the electrons in the metal ligand bonds belong to the ligands. So what we're asking is basically how many, nobody thinks of d electrons on metals as lone pairs, but that's one way to think of it if you want to. We want to know how many d electrons cobalt has. Now, cobalt normally has 9 valence electrons. But its oxidation state is +3. So how many d electrons does cobalt actually have? 6. So we'll say it's a D6 metal. Now, somebody asked in the 9 o'clock hour, did I press record? I really hope I did. Yeah, I forgot to press record in the 9 o'clock hour, so oh well. Somebody asked in the 9 o'clock hour, hold on, aren't the first 2 electrons in a 4s orbital? Doesn't cobalt only really have 7 d electrons? And that would be true for metallic cobalt, but it turns out that when cobalt is bonded to ligands, the relative energies of the d orbitals versus the 4s orbitals switch, and the d orbitals get lower in energy, and so all of the valence electrons go into the d orbitals. That's something you don't necessarily need to worry about, but if you were worried about it, the answer is in a complex, the ligands make it so the d block is lower in energy than the 4s orbital. Okay, so cobalt is a D6 metal. Now we also want to get an idea of what the total number of electrons are around the metal, including ligands plus d electrons. So we've got 6 d electrons and then 2, 4, 6, 8, 10, 12. We've got 6 ligands times 2 electrons per ligand, and we have 6 d electrons. Overall, that means 18 electrons total. Now, if you look at that row of the periodic table, the 4th row, and count the number of columns from potassium all the way through to krypton, there are 18 columns, 18 electrons. You've learned about the octet rule, and for transition metals, they have an expanded octet, but there's still a limit, and the limit is 18. If you have 18 electrons, you get a noble gas configuration. All of the orbitals are filled. And so we will call this complex coordinatively saturated, meaning there's no additional space for more ligands. There's as many ligands on there as you can possibly get. You might have looked at that cobalt and said, why don't I throw on a couple more ligands? And the answer is there's no space for them because you've already filled the 18 electron limit. Yeah?
Are the 6 d electrons that are involved with the cobalt not in the bonds at all?
Right, that's key. So the 6 d electrons that are on cobalt are not in these metal ligand bonds. The metal ligand bonds, those electrons count as belonging to the ligand. And so if we wanted to draw those 6 electrons on cobalt, I suppose you could do this. Nobody does, but you can. Yep. Okay. Let's do that a couple more times with some of the complexes that we've already done. So let's look at tetrakis triphenylphosphine palladium. The palladium with 4 triphenylphosphine groups attached. Those are all L-type ligands. So palladium normally has 10 valence electrons. It's got 4 L ligands. They are all neutral. The complex overall is neutral. You can tell that because I didn't write a charge. So what is the oxidation state of palladium here? +1, +2, +3, -2, what is it? Pull the ligands off. The ligands are all neutral. The complex was neutral to begin with, so the metal must still be what? Neutral. So that's palladium 0. That means, what is the d electron count for palladium? Normally has 10. Its oxidation state is 0, so d10. That's easy. And then total electron count. 10 d electrons, and then 2, 4, 6, 8. So 18. Is there any space for any additional ligands? No. So you could look at palladium and say, why doesn't palladium have 6 ligands like the cobalt 3+ complex? And the answer is, there isn't any space for it. It's coordinatively saturated. So you can use some of this comparison to get an idea of what's possible for one metal versus what's possible for another. Let's do real quick this complex that we did earlier. This is palladium bonded to what kind of ligands? What do we got? 2 are L and 2 are X. The overall complex is neutral. What is the oxidation state on palladium? Okay, how do you know it's +2? How did you do that math? It's neutral. Were you raising your hand?
Oh, no, sorry.
Oh, you were just gesturing. Okay, sorry. Or if Jedi mind trick. Its overall complex is neutral. 2 of the ligands are negatively charged. Therefore, to balance it out, the palladium has to be +2. All right? So palladium 2. D electron count. Palladium normally has 10. If its oxidation state is +2, it must be what? 8. And then total electron count. 8 d electrons, then 2, 4, 6, 8 from the ligands, that's 16. All right. So with that in mind, you now have an idea of figuring out what's possible in a reaction just by being able to count the number of d electrons that are on a metal and the total electron count on a complex. On my final exam, I will expect you to see a complex. You'll have a periodic table, and you'll have to tell me what the oxidation state on the metal is, what the d electron count is. Yes?
So what counts as saturated?
The limit on these complexes is 18 electrons. If it's 18, if the total count is 18, it's coordinatively saturated. That means there's no room for an additional ligand. Yes?
When you do the math for calculating the total number of electrons, is it always going to be 2 electrons per ligand?
Yeah, it's always going to be 2. When you do the math to do total electron count, each metal ligand bond is 2 electrons. Yeah?
How do we count the number of d electrons?
You count the number of d electrons by figuring out the number of valence electrons an atom has. So in the case of the most recent complex we did, palladium normally has 10. Its oxidation state is +2. That means it lost 2 electrons, so 10 minus 2 is 8. Yep, others? All right, now some of you are saying, I'm not even going to take your final because I'm going to do well on the ACS exam. And I encourage that if you can pull it off. But if you can't, you'll want to have the backup plan of taking my exam, in which case you'll want to know this, all right? All right, let's go back to copper then, the cuprate chemistry. I guess I'm flattered that you guys think I'm scarier than the ACS exam, sort of flattered by that, so I feel okay. All right, let's look at the copper prior to the reaction, and let's see if we can figure out what's going on. So if we analyze copper in the same way, the overall charge on this complex is -1. We have 2 X-type ligands here, so therefore, what is copper's oxidation state? Take 2 ligands away, it's -2. The overall charge on the complex is only -1. So copper's got to be +1. And you'll notice, I mean, when we originally did stuff with cuprates, we drew a negative formal charge on copper. You can see how that's sort of deceptive, right? Because actually, the negative charge there would seem to indicate that, oh, copper is electron rich. Well, it's actually in its +1 oxidation state, so it's somewhat electron poor. That's why we drop formal charge in organometallic complexes, because it's not that informative. All right, let's do d electron count and total electron count. Copper normally has 11 valence electrons. It's +1, so it's got to be D10. And then total electron count is 10 plus 2 plus 2, that's 14. So we infer from this copper's +1, and we're not at 18 electrons, so there's room for additional stuff. And that ends up being important because the first step of this reaction, I'll draw the molecule that forms next, looks like this. As you look at that, you may say, hold on, what's going on and where did all of those electrons come from? So let's go through this bit by bit. Now, what kind of ligands do we have? All four X-type ligands. All of these, if they left, would be negatively charged. So we have 4 X-type ligands. Therefore, the oxidation state on copper is what? Gotta be 3. How do you know it's 3? Because the overall charge is minus 4 negatively charged ligands. The only way to balance that is if copper is now at +3. That tells you that this reaction step was an oxidation. And it was also an addition reaction because our starting material, the aryl halide, got added to the metal. So we combine these 2 terms together and we call this reaction oxidative addition. Copper lost 2 electrons. Where did they go? Well, let's see if we can work that out. If copper is +3, how many d electrons does copper now have? 8. So the 2 electrons that we lost were d electrons from copper. The total electron count for the metal is 8 on copper and then 2, 4, 6, 8 from ligands, so 16. How did copper lose 2 electrons, but the electron count went up? Go ahead.
Would it be fair to say that the 2 ligands stole the electron?
Would it be fair to say that one of the ligands stole the electrons? Yes. Okay, so let's figure it out. And this is going to be tough to see because nobody draws lone pairs. But the 2 new metal ligand bonds, you've got 4 electrons two in each of those bonds. Two of those electrons come from the carbon-bromine bond. It's impossible to say which is which is going to irritate you. It drives me crazy, but it's impossible to know. If you want, we can say, oh, well, it's these ones. And then the other two, where did they come from? Those are the two missing electrons when we go from D10 to D8. In other words, those were these lone pair electrons. Two of the D electrons on copper are now in a metal ligand bond, and that's the oxidation. We count the electrons in that bond as belonging to the ligand, even though they came from the copper to begin with. Copper loses those electrons, they go to the ligand. Now, nobody pushes arrows for these kinds of reactions. It may help you to do so, but this will simply be a mnemonic device. You could push arrows from the copper to the carbon, and then push arrows from the carbon-bromine bond back to the copper. And that indicates one way of looking at it. It would be just as correct, however, to push these two arrows to the bromine, and then these two arrows, and then the electrons from the carbon-bromine bond to the copper. We don't have a way of labeling electrons to tell which go where. We do have a way of labeling atoms with isotopes. We don't have that for electrons, so we just can't know. All we know is that two of the electrons in those two metal ligand bonds come from the metal. If you want an idea of what the transition state looks like for this reaction, it's probably not going to help. But I'll draw it for you. It involves three things happening at once. Metal ligand bonds being formed at the same time as carbon-bromine bond is breaking. So that would sort of be the transition state, which I'll put the double dagger on. Okay, that's an oxidative addition. Now, see if you can predict what's going to happen next, because the product has a new bond between the benzene ring. There's the new bond between the benzene ring and then one of the other ligands on the copper. So this step is called a reductive elimination. We're going to eliminate the benzene ring and then one of the alkyl ligands on the copper. And at the same time, the copper complex is going to get reduced. What's left on the copper after this reaction is just one of the alkyl ligands and the bromide. And if you go through the same process, you will see that copper is now back at +1. It now has 10 d electrons, and its total surrounded by is only 14. So you can infer by this that we took two of the electrons in one of these ligand metal bonds and we used them to make the new carbon-carbon bond, and then the other two electrons went back to copper. And you can choose to push arrows if you want. You can choose to push arrows like this to form the new carbon-carbon bond, and then these electrons go back on the metal. You could draw them totally in the other direction. You could draw it this way and this way. There's no way to tell the difference between the two. So however you want to make it happen is fine. Nobody pushes arrows for these steps. I'm simply showing you to give you an idea of what's going on. And then after the reaction, those are the two electrons that are now back in the d orbital. So that's oxidative addition and reductive elimination. And those are two key mechanistic steps, two key reactions that transition metal complexes can do that you've never seen before. And those are really important in the new reactions we'll talk about in this chapter. Okay, questions so far? All right. So now let's talk about a Nobel Prize winning reaction. We leave it to the end, and it's kind of a shame because of all the reactions we've talked about in this semester, this one by far is the one most used in the pharmaceutical industry to make new molecules. It works really, really well. And this is called, a lot of these reactions are named for their discoverers. So this is called the Suzuki reaction, named after Professor Suzuki who discovered it. And it is, they call it a cross-coupling reaction because you take two different things and you couple them together, making a new carbon-carbon bond. So one of the starting materials is usually an aryl halide. It's got an sp2 hybridized carbon halide bond. In your text, that halide is often a bromo, it can be iodo. Chloros don't work quite as good, but some people are still working on that. Then the other partner is an unusual functional group that you haven't necessarily encountered yet, either a boronic acid or a boronic ester. What that is it's a carbon bonded to a boron where the boron is also bonded to two oxygens. In the boronic ester, the two oxygens are OR groups. In the boronic acid, the two oxygens are OH groups. The thing that's attached to the boron is either vinyl or aryl. So it can be a benzene ring or it can be alkene carbon. The important thing is that it's sp2. The reaction conditions are a palladium catalyst. In this case, it's the tetrakis triphenylphosphine palladium. That means 4 triphenylphosphines attached to palladium. And you also need a base, and sometimes this is sodium hydroxide. Sometimes it can be a nitrogen, it can be an amine base, it sort of depends, and a lot of people have tried a lot of things work. The product makes a new carbon-carbon bond between the orange sp2 hybridized carbon on the benzene ring and the blue sp2 hybridized carbon on the vinyl group. And importantly, stereochemistry is on the vinyl group is preserved. If the boronic acid or ester is trans, the stereochemistry of that double bond in the product must also be trans. If it is cis, the stereochemistry in the product must also be cis. Okay, so that's why they call it a cross-coupling reaction. Once you recognize the Suzuki reagents and the starting materials, the Suzuki reaction is easy. It's one of these Lego reactions. You simply pop the ends off and stick the two parts together. And so predicting the products become easy once you've worked with the reaction enough. What's challenging here is to figure out what on earth is going on in the first place and how does this reaction happen. So we're going to go through the mechanism because it's an example of oxidative addition and reductive elimination. And on my final exam, I expect to be able to show you a mechanistic step like this and ask you, what was that step? And I expect you to be able to tell me that was a reductive elimination. And the way you can do that is by monitoring the oxidation state of the metal. All right, so let's talk about mechanism. All right, you start out with that triphenylphosphine palladium complex, but like we showed you before, the problem with that complex is even though it's palladium 0 and it's got 10 d electrons, there are 18 electrons total. So that metal is coordinatively saturated. That means there's no additional ligands that can bind, which means nothing can happen. It turns out the thing you put into the reaction isn't the active catalyst. because it's not got space for anything to happen. Now, ligands in transition metal complexes, there's some equilibrium constant that governs them falling on and off. And at some rate, you can lose 2 triphenylphosphine ligands. When you do, the complex is still neutral, but it is now still palladium 0, but now it only has, and it still has 10d electrons, but now it only has 14 electrons total because we lost 4 electrons with those 2 ligands. So now there's open spaces for the chemistry to happen. Enter our starting material, the aryl halide. And that adds to the metal to form the following complex. Overall, the charge on the metal is still neutral. Let's analyze that. How many and what type of ligands do we have? You got 2L and 2X. The overall charge on the complex is neutral. Therefore, what must be the oxidation state of palladium? Now has to be 2+. That means it's D8. And we can count the overall electron count. It's 16 electrons total. That means this was an oxidative addition step. You can tell that it was an oxidative addition because 2 things on our starting material got added to the metal, the phenyl group and then the bromo. Of the 2 bonds in between ligands and metal that we just added, 2 of the electrons come from the metal and 2 come from the carbon halide bond. And it's impossible to say which, but I'll just color them differently so you know 2 came from the metal and 2 came from the carbon halide bond. Okay, that's the oxidative addition step. Now, the next step is a little bit challenging. It's called, one way to think about it is to call it ligand exchange. The people that know a lot about the Suzuki reaction call it a transmetallation reaction. This is where our second starting material comes in. So here's the vinyl group, which I guess we colored that vinyl carbon blue. And it turns out that the purpose of the hydroxide base is probably to bind to the boron to make the boron electron rich. And the boron is pretty anxious to lose the vinyl group so that it can be neutral again. And so what ends up happening is a swap between the boron and the palladium. The boron's going to come away with the bromo, and the palladium's going to come away with the vinyl group. So let me draw what happens after that swap. Here's the vinyl group now attached to the palladium. And then over here you now have the boron and the halide attached to it. So the precise mechanism of that step is not really well understood. We won't worry about it, but we will notice that we still have 2 X ligands. We're still palladium 2+. We still have D8 electron count on palladium, and we still have 16 electrons total. At this stage, you can maybe, based on the cuprate chemistry, have an idea of what's going to happen next. If we do a reductive elimination step, we can use 2 of the metal ligand electrons to form a new carbon-carbon bond between these 2 ligands, and then 2 electrons will go back on the metal. And that's exactly what happens. This next step is reductive elimination. And here is the new bond we just made between the carbon of the benzene ring and the carbon of our vinyl group. And again, if you want to think about these two electrons as being different, you can push arrows if you like, showing a new bond here and then this bond breaking, or you can do it the other way. Either way is fine. And then you will notice then that that reductive elimination step takes us back to our starting catalyst, which is now palladium 0 with 10d electrons. So one of the reasons palladium can do this is because it's really electron rich. It's got 10d electrons. It's happy to donate two to a ligand temporarily. And then it's also happy to get those electrons back. Okay, questions about that mechanism? Yes?
Can reductive elimination only happen between two X ligands?
Can reductive elimination only happen between two X ligands? That's a great question. At least that's the only times I've shown it to you today. I don't know whether that's a true limitation or not. It's a good question. Yeah?
Will it always be oxidative addition and reductive elimination, or could it be reductive addition and oxidative elimination?
Yeah, would it always be oxidation first and then reduction second? I think so. You could imagine a situation where a metal would do reductive elimination first. Yeah, it's possible that's, I can't think of any counterexamples, but that's just because I don't know a lot about this area of chemistry. So for the reactions we do, oxidative addition will usually precede reductive elimination. Okay, good. Other questions? Yeah.
And it's oxidative because we're increasing the number of heteroatom bonds, or?
So why is it oxidative? In organic chemistry, we think about oxidation as increasing carbon heteroatom bonds or decreasing number of carbon-hydrogen bonds. Here, we're falling back to the initial, earlier, simpler definition of oxidation, which is loss of electrons. So what's getting oxidized is the metal. It goes from D8, used to have 10, D10, sorry, that number is 10, not 8. Used to be D10. After oxidative addition, it's only D8. So that's the loss of electrons. Where did they go? They went into the metal ligand bond. All right, others? Yeah?
This goes back to a little bit earlier, but I'm confused how the vinyl carbon can be an L-type.
How can the vinyl carbon be an L-type ligand? Sure, let's look at that in this intermediate. Just imagine if it left with its electrons, what would it be? It would be an anion. That would be a really unstable anion, but we count. The other thing to remember is we count all the metal ligand electrons as belonging to the ligand.
Isn't that an X-type ligand then?
Yes, it's an X-type ligand. Did I say L?
You said L earlier.
I apologize for that. Yeah, no, let's be absolutely clear about this. 2 L-type ligands, 2 X-type ligands. Yeah. Okay, good. Others? Yeah.
How do we tell the number of total electrons?
So to determine the total number of electrons, you first need to know the oxidation state on the metal. That gives you the d electron count. And then you add to those 8 d electrons in this case, all of the metal ligand bond electrons. Okay, well, let's call that good. Next time's last time, so hang in there, and I'll see you on Wednesday.